Hi folks, we're going to be going over the TENS, which is balancing equations, introducing you to this new topic. So we're going to go right through the worksheet. It says in a chemical reaction, the compound water is synthesized from the elements hydrogen and oxygen. Recall that both hydrogen and oxygen are diatomic elements. That means they're always in pairs. Those are two elements that always need another one. So H always needs another H to be pure hydrogen. Oxygen needs another oxygen to always be pure oxygen. So if we read this balanced equation, it says 2 moles of hydrogen gas. So that's what this is. Sometimes we'll say 2 moles of hydrogen. Don't let the word gas freak you out. With 1 mole of oxygen gas produces 2 moles of water. If you look right here, there's nothing in the blank. If there's nothing in the blank, we assume there is a 1. If it really bothers you, you could put a 1 there if you needed to do so. The big numbers before the chemical formulas, these right here, these are called coefficients, and that's what this unit is kind of all about. And these small numbers right here, which we've already introduced you to, those are called subscripts. So notice the number 1 for 1 mole of oxygen is not shown, but the 1 is implied. If you want to put a 1 in there again, you can do so. You'll see most textbooks will not put a 1 in that spot. This arrow right here that separates the two, that separates the before and the after reaction, and that's read as yields or produces. So we would say 2 moles of hydrogen gas and 1 mole of oxygen gas produce or yield 2 moles of water. These items over here are called the reactants. A lot of people will get that mixed up, but those are the things that are actually reacting together to make the product. So the reactants are over on the left side, and the products are over on the right side. Many people will get that mixed up. And I think we got that all right there. So again, reactants are found on the left-hand side and the products are found on the right-hand side. The reactants react together to make the products. So we're looking at this particular chemical reaction. This is the above reaction can be read 2 different ways. Fill in the blanks. Well, I kind of already let the cat out of the bag. 2 moles of H2 are reacted with 1 mole of O2 to produce 2 moles of H2O. That's one way of reading it. What is H2? Is that an atom? No, it's not. It's a molecule. So we can put that in here, molecule. And there is no abbreviation for molecule, just so you are aware. So 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to produce 2 molecules of water. Some instances we could put atoms in the blank, but it's very rare. But it is possible that we could put atoms in the blank, but probably not for all of them. Those atoms are going to react together to make a compound, and that compound would in fact be called a molecule then. And later on in semester 2, we can read this as 2 liters of hydrogen gas react with 1 liter of oxygen gas to produce 2 liters of water. But that'll be later on in the year. And you don't need to know about that right now. So number 11. We are going to try to find out if the mass of this stuff equals the mass of this stuff. And if we look at this, we see that there's 4 H's here, and there's 2 O's here. And over on this side, we have 4 H's here, and this 2 goes all the way through, so we end up having 2 oxygens there. Nothing is added, nothing is removed. Whatever we start with is there at the end. And we want to find out if the grams of this stuff equals the grams of this stuff. So here we go. This is how we would go about solving this particular setup. You have this on your page. It says calculate how many grams there are in 2 moles of hydrogen gas. So we start with the 2 moles of hydrogen gas. That 2 comes from right there. So moles of H2, we put moles of H2 on the bottom, just like we've done in our last unit. And we can go from moles to grams. We learned how to do that in our last unit. But this is H2, it's not H. So H2 is 2.00 grams in 1 mole of H2. So that's one little difference that we have. So if we do the math on that, this has infinite sig figs. This has 3 sig figs. This 1 in front of the mole is always going to be infinite sig figs. So 2 times 2 is 4.00 moles of H2. Please try the next 2 before I go over them. So pause the video and try the next 2. So how many grams are there in 1 mole of oxygen gas? So I start off with the 1 mole of O2. Multiplication sign, division bar, whatever's on top goes on the bottom of the next step. Moles O2. I can go from moles to grams of O2. Where do I get that information? I get it off the periodic table. But it's not the mass of 1 O. It's the mass of O2. And that would be 32.00 grams in 1 mole of O2. You solve that, and you end up getting 32.00 grams of O2. Checking sig figs. This is not going to be looked at because that's a given value. We're not going to look at that. This is infinite sig figs. This is 4, so we should have 4 sig figs in our answer. Again, please pause the video and see if you can do the next one on your own. Calculate how many grams there are in 2 moles of water. So the 2 is coming from right up here. So we start off with 2 moles of H2O, multiplication sign, division bar, mole H2O, gram H2O. This is nothing new. This is what we learned in our last unit. The mass of water is 18.00 grams per mole. That's the mass of 2 hydrogens and 1 oxygen. So we have 18.00 grams in 1 mole of oxygen. You do the math on that. Infinite sig figs, 4 sig figs right there. So our answer is going to have 4 sig figs. So if we do the math on that, we get 36.00 grams of H2O. So let's figure this out. We had 4.00 grams of hydrogen. And what did we have for the oxygen? We had 32.00 grams of oxygen. And if we do those two together, if we add those two together, that gives us 36.00 grams on that side. And we figured out over here that this is 36.00 grams. So 36.00 grams went into the reaction, 36.00 grams of reactants reacted in a chemical reaction and made 36.00 grams of product. This is called the conservation of mass. So you need to write this down. It's a kind of a big thing in chemistry. I wrote it in red, the things you need to write down, that mass is neither created nor destroyed in chemical reactions. So all the atoms we started with are there. All the atoms are there when we finish. Those atoms have mass, and therefore mass is neither created nor destroyed by chemical reactions. And that's under normal circumstances, stuff that we can do in a classroom. Yes, there are universities that can actually destroy atoms and create atoms. We are not one of those facilities. So whatever we start with, you finish with. There's also the law of conservation of atoms, which state that atoms can neither be created nor destroyed. And both of these laws are very similar to each other because if the atoms are not created nor destroyed, and those atoms have mass, then the mass is not created nor destroyed. And therefore, the two are kind of the same thing, just using some different words. So, got to flip the page. So, in this first question on the next slide, I'd like you to try to answer as much as you possibly can. If you do have some questions, you can ask us some questions, but pause the video, see how much you can get done, and then play the video and see if you are in fact correct. So explain why subscripts are not altered in the process of balancing a chemical reaction. So here I have two H's, and here I have two O's, and over here I have two H's, and I only have one oxygen. So the simple thing you might want to do is just simply take, sorry about that, take and put a 2 there. And now I have two O's on each side. But this compound right here is called hydrogen peroxide. Maybe you've used it at your house before. Maybe you bleached your hair with it. Maybe you had a boo-boo on your finger that had some blood on it, and somebody put some hydrogen peroxide on it and it bubbled. That's hydrogen peroxide, which is quite different than this stuff, which is called water. You don't take a shower and all of a sudden your hair bleaches out on you. So water and hydrogen peroxide are different from each other. So we can't just modify subscripts. We're not allowed to do that. When a balanced equation is read, name two ways that the coefficients can be interpreted. So those are those big numbers out in front, like 2H2O. This is a coefficient. How can that be read? Well, I can read that as 2 moles. And I can read it as 2 molecules, and sometimes I can read it as atoms in some chemical reactions, but very few. What do we call things on the right side of the arrow? So here's my arrow, and if you have trouble with directions, this is the left side. So this is the left side, and this is the right side. Again, we go through this because a lot of people get this messed up. So what's the stuff on the right side? What is the stuff on this side called? And that would be a product. And what are the things on the left side called? Those are called reactants. And what does the arrow mean? It means to yield or produce the stuff, the products. What does combustion mean? Well, combustibles, a combustion reaction, internal combustion engine. All those things mean to burn something. What reactants are needed for combustion to occur? Well, if you don't have oxygen, you can't have the reaction occur. And then we define combustion as basically carbon burning with oxygen or reacting with oxygen. And what are the products of combustion? Carbon dioxide and water. And we hear about the internal combustion engine producing a lot of CO2, leading to global climate change. So now we're going to balance our first reaction. So what we do here is we can look at all these blanks and we can assume there's ones in them. So if you feel better and you want to put ones in all of them, you could. That's absolutely fine. If you don't want to put ones in them, which I don't do, Mr. Barazin doesn't do, but if you want to do that, you absolutely could do so. And then what we do is we state all the elements in the compound, or in the chemical reaction, I should say. And now we're going to count them. So how many carbons do I have on this side? Well, I have 1 carbon. And I go over to this side over here on the product side, and I have 1 carbon. And now I go to hydrogens. I have 4 hydrogens on that side. And how many hydrogens do I have on this side? Well, I have 1 in front, so that means I have 1 H2O. So I have 2 H's on that side. How many oxygens do I have? I have 1 O2, so that's 2 O's that I have. And on this other side, I have 1 O right there, and I have 2 O's right there. So I have 3 O's on this side. Now I'm going to erase some of the stuff that I have here. If you don't understand where I came up with the numbers, I would pause the video, rewatch it, make sure you understand where I got those numbers from. Otherwise, you won't understand what's going on. So what I need to do is I need like a teeter-totter. You ever played on those as a kid? You know, you put one child over here and they go down, and that makes this child over here go up. Well, we don't want it to go up or down. We want it to be perfectly balanced. So we got to look at this. The carbons are balanced, the hydrogens are not balanced, and the oxygen is not balanced. Now, here's a little trick. In most of these problems, we want to save hydrogen and oxygen for last, and we absolutely want to save diatomics for last. That is the last thing that we should be trying to balance in this equation. So using that philosophy, we want to save oxygen for last, we go to hydrogen. So how do I make sure that there's 4 H's on this side of the reaction? The only thing I can do is put numbers in these blanks to change that. So what I'm going to do is I'm going to put a 2 here. 2 H2O's are like writing H2O, H2O. So in 2 H2O's, I have 4 H's now. So I cross out that 2 and I put a 4. Now my carbons are balanced and my hydrogens are balanced. But my oxygens, I have 1 oxygen there, I have 1 oxygen there, and I have 2 oxygens there. So now I have 4 oxygens on the right-hand side. So I need that to balance. So I need to go over here and change something. So I'm going to put a line through that. I'm now going to say I have 2 O2s. That's like saying, okay, that's 1 O, and that's another O. So that's O2, and I need another O2. So I need another O and another O. So that's 4 O's that I have now. And so I cross out that 2 and I put a 4 there. And now I am perfectly balanced. So when I have 1 methane molecule and 2 oxygen molecules, I make 2 water molecules and 1 carbon dioxide molecule. And we can watch this reaction. This is called a combustion reaction. So what these guys are doing is they're on a lake where there's a lot of decomposition occurring in the water, and that creates methane gas. And the methane gas is bubbling up to the water, gets to the top, and it freezes into these pockets. So they go out there with a lighter and they light the methane gas on fire in a combustion reaction. So watch these guys for a little bit. It is dangerous if you do your face too close to it. They obviously do not know the direction that the wind is blowing because they would put themselves on the other side so the flames were not flying directly at them. And yes, we do have lakes in Wisconsin that you can find methane gas that's being produced like this. And if you want to watch more methane bubbles, you can go online to YouTube and type in methane fireballs and watch more of them. All right, so here is another one. So what kind of reaction is this? Again, we have carbon over here. We have oxygen over here. This is a combustion reaction. So in a combustion reaction, what is always made? Water and carbon dioxide. This time I'm going to put the CO2 in front because it doesn't matter the order that they go in. So I don't want you to start feeling like water's always got to go first. So what we have to do now is we have to count up how many of each element that we have. This time I'm not going to put ones in all the blanks, but if that is what you would want to do, you absolutely could do that. So I'll put carbon there, hydrogen there, oxygen there. I'm going to count up of what I have of each one. So here I have 3 carbons. And on this side right now, if there's a 1 in this blank, I have 1 carbon on that side. And how many hydrogens do I have over here on the reactant side? I have 8 of those. And how many do I have over here on the product side? Well, again, I'm assuming there's a 1 in that blank. So I have 2 H's on that side. And how many O's do I have? I have 2 here and a 3rd one here. So I have 3 O's or 3 oxygens. And on this side, I have 2 oxygens there and I have 1 oxygen there. So that's 3 oxygens. Now I'm going to do a little erasing, clean things up a little bit. So now I have my setup. I do want you all to realize that this whole setup is math. It's a way of keeping track of things. It's never corrected. It's never looked at. When I change a number down here, it does not change a number up on top. It simply is a way of keeping track of everything. So do realize that you have to change something up in these blanks to actually make something happen. So the first thing I look at the carbons. I have 3 carbons there. I got 1 carbon there. So if I simply put a 3 there, now I have 3 carbons on each side. But since I added 3 CO2s, that's like going CO2, CO2, CO2. That's what I just did. That also changed my oxygen. So how many oxygens do I have here? Well, I have 2, 4, 6, plus that one up there. That's my 7th oxygen. So my oxygens are now at 7. Again, pause the video at any point in time you need to look over this information. Now my hydrogens. I'm going to clean this up a little bit. My hydrogens are not balanced. So how do I get 8 hydrogens over here on the product side? Well, if I put a 4 there, that's like going H2O, 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 H2O. I now have 8 hydrogens. But that changed my oxygens as well. Now I have 4 oxygens here. And right there, I have 6 oxygens. So that's 10 oxygens overall. So I keep crossing out my math counter down here as I'm going along, changing it to make sure that I have the same number of things on each side. So everything's balanced in this problem except for the oxygens. So now let's look at the oxygens. So I have 3 on this side. So if I put, let's put a 4 here, that would be O2, 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 and that gives me 8 O's. I probably should make that a little different there. So 8 O's. And I have 1 right here. So that's 9 O's overall. But I need 10. Okay, so let's not do a 4 there. Let's do a 5 there. So now I have O2, O2. That's 10 plus this 1. That's 11 O's. I need 10 O's. So when I had a 4 up here, I didn't have enough oxygens. When I had a 5 up there, I had too many oxygens. What's between 4 and 5? And this is called the 0.5 method. The answer is 4.5. So what does that look like? Well, that's 4 O's plus a half of an O, which is just an O, plus this O comes in. So now I have 2, 4, 6, 8, 9, 10 O's. And everything's balanced. But we can't really have half of an O2 molecule. So what we do now is there's a 1 there. We multiply the whole thing by 2. And you can put the 2 there, you can put the 2 in the front, it really doesn't matter. But we multiply the whole thing by 2, and we end up crossing out that number and putting a 2 there, and 4.5 times 2 is 9, and 3 times 2 is 6, and 4 times 2 is 8, and the whole thing balances out. If you're at home, this reaction is basically alcohol starting on fire. What kind of reaction would that be? That would be a combustion reaction. Again, we produce carbon dioxide and water. So here's our last reaction that we're going to work on today. This is what you see when tracer rounds, if you've ever watched any kind of military shows and you've seen them shoot and you see this kind of like flare, kind of streaky color come out of the guns. This would be where the phosphorus in the bullet comes in contact with the oxygen and gives off a bright flash, and you can kind of trace where your bullets are going then. So if we look at this one, how many P's do we have on the left-hand side, the reactant side? There are 4. And how many P's do we have over on the product side? There are 4. That's nice. Oxygens, right now we have 2 O's over on the reactant side, the left side. And on this other side, we have 10 O's. So this one, all we have to do is change it to a 5, and all is good, and we are balanced. And throw 1s in there at the very end. We are balanced. Now, this chemical reaction is also an experiment or demonstration called barking dogs. So we'll watch barking dogs.
Covered with pieces of filter paper. A solution of bright phosphorus dissolved in carbon dioxide. Watch and listen, focusing your attention on both the paper and the cylinders.
And that is called barking dogs. That is phosphorus reacting with oxygen. What type of reaction is this? Well, we have 2 things coming together to make one new thing, and that's called a synthesis reaction. I want to tell all of you folks that the reactions that we have at the top of your page called synthesis, decomposition, single displacement, double displacement, combustion, and neutralization, we'll use on a couple worksheets, but we'll never ask you about that on the test. It's something you kind of should be familiar with, but it's not something that you need to know right at any one moment. You might use it in college a little bit. And that is all we have for today. So thank you very much for tuning in.